Hello everyone, Oleg is here. Welcome back to our calculus series. In our previous video, we transitioned from abstract mathematical concepts of sequences and sets to their practical implementations in Python. We explored lists, tuples, and sets, and examined common set operations in both mathematical notation and Python code. Today we'll examine the behavior of numerical sequences more closely. We'll discuss what it means for a sequence to be bounded or unbounded, and then explore the concepts of sequences that become infinitely large or infinitely small. These ideas are crucial for understanding the concept of limits, which we'll tackle in future videos. Reminder about the sequence notation. A sequence is defined using the following notation. It is read x sub n or x nth, where n is the natural number, which is the index of an element, and x is the actual element. Here is how we're going to show elements of a sequence. For example, the horizontal axis may be the natural numbers or the indexes of the elements, and the y-axis will be the elements themselves. So on the y-axis we have the values. These may start from, 10, 11, and so on, but these at the same time may be 1, 2, 3. This may be any scale actually. And these are the indexes. For example, the first one element may be 1, the second element may be 2, the third element may be 3, and so on. And this is the sequence where each element is equal to its index. So this is the sequence n. So let's talk about the concept of boundedness. A sequence is said to be bounded if all of its terms lie within a certain range. We can define boundedness from below, from above, or both. We can see easily that this sequence on the image, on the graph, is bounded below or bounded from below by 1. So there are no elements which are less than 1, and we can draw imaginary line, horizontal line. This means that there is some border for this sequence. And we'll start talking about the bounded below first. A sequence x sub n is called bounded below if there exists a number m such that every element of the sequence is above it. In other words, this satisfies the inequality. Every element is more or equal than m. So this is the definition of bounded below. This means that we can find some floor value that the sequence never goes below. In our case, for example, this may be 1. We can express this formally using mathematical notation. This is the mathematical notation of boundedness below. The symbol, this one, is called existential quantifier, means there exists. So there exists such m small, from the set of real numbers which we covered in the previous videos. And this symbol is called universal quantifier, means for all. For all numbers from the set of natural numbers, we discussed this also in the previous videos. And this column means such that. How it's read all together. There exists a real number m that for all natural numbers x nth is greater than or equal than m. To put it a bit simpler, there is some border from below that for every index the value of the sequence will be above this border. And this fits our case. So our sequence here, as a reminder, is equal to the index, and we can see that every element is above this border of 1, so m equals 1. This means that this sequence is bounded below by 1. In the same way, a sequence is called bounded above if there exists a number such that every element of a sequence satisfies the inequality that every element is below this number. This means that there is some kind of a ceiling that no value of a sequence never goes above. And here is an example. There is a sequence starting from 4 and going below, and we can see that it is never above the ceiling. So this is bounded above. The mathematical definition is similar. There exists such m large, which is a real number, such that for every natural number, elements of the sequence are less than or equal to m capital. And let's consider an example. An example of such a sequence may be these negative numbers, for example, minus n, and we can draw this. So for the first element, this will be -1, for the second, -2, for the third, -3, and so on and so forth. And you can see that this is bounded above by -1. So this means that this sequence is bounded above. Finally, last but not least, a sequence is bounded if it is both bounded above and bounded below. This means that all terms of the sequence are trapped within a certain interval. Here is an example of such a sequence. This is the sequence where each element is -1 to the power of index to the power of n. So the first element will be -1, the second one is 1. So even elements will be above and the odd elements will be below. And you can see that they are surrounded from both sides. So this is the bounded above and this is the bounded below. So all elements are within this range. The mathematical notation is similar, but now there exist two numbers, m and m large. They are real numbers, such that for every natural index, which is a natural number, the following inequality holds. X nth is within this interval. We can also express this in a bit different way using the absolute value. So the absolute value of x nth will be less or equal than a, where a is the maximum value of the absolute values of m and m large. And let's read this once again. There exist real numbers m and m large such that for all natural numbers n and small, the value of every element is more or equal than m and less or equal than m large. Alternatively, there exists a positive real number a such that the absolute value of every term x nth is less than or equal to a. And the examples of such sequences may be the following. For example, this one, as we have already discussed, or maybe 1 divided by m. So at the value of 1, this is 1. At the value of 2, this is 1/2. At the value of 3, this is 1/3. And so on. This will be bounded by 1 from above and by 0 from below. And overall, this sequence is bounded from both sides. A sequence is unbounded if it is not bounded. This means that either not bounded above or not bounded below, or neither. In other words, the terms of the sequence go beyond any fixed upper or lower limit. On the screen you can see an example of kind of oscillating sequence which starts from -1, then 2, then -3, +4, -5, and so on and so forth. So you can see that this oscillates to kind of infinity. So this means this will be unbounded. And the mathematical notation is similar. For every positive value a, there exists such a natural number such that all the elements will be more than a. And again, for all positive numbers a, there exists a natural number n such that the absolute value of the element with this index is greater than a. And let's try to visualize this on the plot. So let's assume that we are going to take a of 1. So we take a, we say that this is the bound, and this is also from below because we're taking the absolute value of the element. And we can easily find the index of the sequence where this is broken. So we see that starting from the index 2, the bound doesn't work and the sequence becomes unbounded because the absolute value becomes more than a. And regardless how large the a value we take, this will go further and further. And the example you can see on the graph is the following sequence. It's -1 to the power of n multiplied by n. So this is -1, 2, -3, 4, and so on. Note, sequence may be bounded and unbounded at the same time. For example, sequence n is unbounded above, so it goes to infinity and beyond, while it is bounded below. So none of the elements are below the value of 1. And vice versa. The sequence of -n is unbounded below and bounded above. Now let's talk about a specific type of unbounded sequence, those whose terms grow infinitely large. We call these infinitely large sequences. A sequence is called infinitely large or tends to infinity if all its terms eventually become or stay larger in magnitude than any arbitrarily large positive number. To put it formally, for any positive number a, and again we can say that this is a, no matter how big, we can find a point in the sequence after which all subsequent terms have an absolute value greater than a. Note, not elements have to be greater than this value of a, just all subsequent starting from some point. And we can see that the first element is below this arbitrarily chosen a, while starting the second element every further, all consecutive sequences are going to be above this arbitrarily chosen a. Mathematical notation is the following. For any arbitrarily chosen positive value of a, there exists such an index n, capital, such that for every index after this, the absolute value of the term is larger than a. And this is very important. For the boundedness, we were talking that the whole sequence is above some value or below, while for the infinitely large sequences, we say that there is some bound index after which all the indexes satisfy this inequality, that all the elements of these indices are larger than any arbitrarily chosen a. And it is important to note that any infinitely large sequence is always unbounded. If a sequence's terms are growing beyond any limit, it certainly cannot be contained within a fixed range. For example, this one is a sequence n squared, where each index is multiplied by itself for each element. And you can see that it has no limit, so that's why it's infinitely large sequence. And it certainly cannot be contained within a fixed range. However, an interesting case, the sequence minus 1 to the power of n multiplied by n is unbounded, but not infinitely large. So every infinitely large sequence is unbounded, while the opposite doesn't work. Some unbounded sequences, like this one, might oscillate or behave in other way without consistently going towards infinity or negative infinity. Let's prove that the sequence n is infinitely large using the definition we have just introduced. The proof may be a bit weird, but this happens frequently in math. Let's take a, which will be any positive number. And we know that from inequality, we can get the following. Because we know that n is positive, we can open the absolute value, so this will be n more than a. If we take n large more or equal than a, which is the positive value, then for all indexes after this n large, the inequality above holds, because n is larger than n large, and large is larger than a capital, so this means that n will be more than a. As a may be arbitrarily large, then, according to the definition we discussed, this sequence n will be infinitely large. In other words, for any a, there will be such an index after which the sequence's values are above. Note, as you may find from the definition, the sequence with negative elements, like this one, is also infinitely large, because according to the definition, the requirement is to be the absolute value larger than a. A sequence is called infinitely small or tends to zero if its terms eventually become and stay arbitrarily close to zero. Formally, for any small positive number epsilon, we can find a point in the sequence after which all subsequent terms have an absolute value less than epsilon. Let's write the mathematical notation and then work with an example. For any positive epsilon, regardless how small it is, there is such n capital from a set of natural numbers such that every index after n capital makes this inequality alive, that the absolute value of an element is less than epsilon. And again, for all positive numbers epsilon, there exists a natural number n such that for all natural numbers greater than n, the absolute value of an element is less than epsilon. Now let's prove that the sequence 1 over n is infinitely small using the definition we just gave. We need to find a suitable n. We need to show that for any positive number epsilon, there is a point n such that for all n small greater than n, the absolute value 1 over n will be less than epsilon. So let epsilon be any positive number as always. And let's consider the inequality 1 over n less than epsilon. Since n is a positive number, then this fraction will also be positive. Then we can open the absolute value, and this will be the following inequality. To solve for n, we can take the reciprocal of both sides. Important note, when taking the reciprocal of both sides of inequality, where both sides are positive, we must reverse the direction of the inequality. So this one becomes n is more than 1 over epsilon. Now let's choose n large to be the greatest integer less than or equal to 1 over epsilon. Which is denoted with square brackets. If n is any integer larger than n capital, then n should be larger than the greatest integer smaller than 1 over epsilon. And this follows that n is larger than 1 over epsilon. Taking the reciprocal again and reversing the inequality, we get that 1 over n is less than epsilon. Which means, because again it's positive, we can take the absolute value. Therefore, for any positive epsilon, we have found an n capital and large, such that for all n and small after this n large, this inequality holds. This proves that the sequence 1 over n is infinitely small. And let's work with some examples. So let's consider this as 1. And for example, for epsilon equals to 1/2, we can find the n large. N large will be the greatest integer less than or equal to 1 over epsilon. This will be 2. So we can say that after the second element, strictly after the second element, the sequence becomes infinitely small, according to the picked epsilon. Let's prove it. The first element will be 1, the second element will be 1/2, and the third element will be 1/3, somewhere here. Our epsilon is 1/2. We can draw this border. And we can easily see that after n equal 2, strictly, when n small is equal to 3, this inequality starts working for this point. Another example of the calculation may be for epsilon, which is 4/15, which is a bit less than 1/3, n will be 3, and we know that the third element is equal to 1/3. This is because we take this sequence, and our epsilon is a bit below 1/3, very bit below. And we know that starting the element 4, so 1 after n equals 3, so when n small equals 4, this will be 1/4, 0.25. The sequence is proving that this is infinitely small. And we can do the same exercise for any epsilon, and this will still work for this sequence 1 over n, proving that this is infinitely small. There's a crucial relationship between infinitely large and infinitely small sequences. If a sequence is infinitely large, for example x_nth, and all its terms are non-zero, then the sequence 1 over x_nth is an infinitely small sequence. And conversely, if this one is infinitely small sequence and all its terms are non-zero, then this one will be an infinitely large sequence. Let's prove the first theorem. The second one is proven in the same way, so we will not do that. Since xnth is infinitely large, then for any positive number a, there is such n large, such that for all indices after it, this inequality holds. This is by definition. Now let epsilon, positive epsilon, be given. We need to show that there exists some n prime such that for all indices after n prime, this inequality holds. And this is again by the definition of infinitely small sequence. This is what we have. We have one infinitely large sequence, and we need to find that the reciprocal of such is an infinitely small sequence. Let's choose a equal to 1 over epsilon. Since this sequence is infinitely large, there exists such n prime that for all indices after it, this inequality holds. This is just the rephrase of this definition. Since both this one and this one are positive, we can take the reciprocal of both sides and reverse the inequality. And we get this inequality. Thus, for any epsilon more than 0, we found such n prime that for all natural indexes, natural numbers, which are indices of the sequence, more than n prime, this inequality holds, proving that 1 over xnth is an infinitely small sequence. Now let's talk about the properties of infinitely small sequences. The first one. The algebraic sum of a finite number of infinitely small sequences is also an infinitely small sequence. So let's prove this theorem by taking two sequences, a_nth and b_nth. They are two infinitely small sequences, and we want to show that their sum is also an infinitely small sequence. Let's take a positive epsilon. Since the first sequence is infinitely small, there is such an 1 that for all indices more than n1, this element is less than epsilon by 2. Why we take epsilon by 2, you will know very soon. We can take any arbitrary number because of the definition of an infinitely small sequence. In the same way, there exists some n2 after which the indexes n of the elements will satisfy this inequality. Let's take n as the maximum of both these natural numbers, n1 and n2. Then, for all indices, natural numbers more than n, both this works and this works. And now we need to consider their sum. By the triangle inequality, this should be less than a sum of absolute values. And because each of them is less than epsilon halved, we can say that they both together are less than epsilon by 2 plus epsilon by 2, because they are less than epsilon by 2, each of them at the same time. Then we can sum them together, and this proves that the sum is strictly less than epsilon. So we can see that for any positive epsilon, we can find n large such that for all indices n small, after this n large, the sum will be less than epsilon, proving that this sum of two infinitely small sequences is also an infinitely small sequence. As I have already mentioned, this works for any finite number of infinitely small sequences. If we add some third infinitely small sequence, the same proof will work. The second interesting property is, of course, about product. The product of two infinitely small sequences is also an infinitely small sequence. We're not going to prove this because the proof is very similar to what we have just proven. An important note about the quotient of two infinitely small sequences. This may be any sequence and may be even not defined if the denominator becomes 0. Let's look at some examples. If both are 1 over n, and as we may remember, these are two infinitely small sequences, the quotient or the fraction will be a constant sequence where each element is just 1, like 1, 1, 1, and so on, which is not infinitely small sequence. If the first one is 1 over n, while the second one is 1 over n squared, then this quotient will be an infinitely large sequence, because 1 over n divided by 1 over n squared will be just sequence n. And vice versa, if we take 1 over n squared and divide it by 1 over n, this will be an infinitely small sequence. And if starting from some index, the terms of the sequence in the denominator are 0, then the quotient is undefined. Last but not least, property. Bounded sequence times infinitely small sequence. The product of a bounded sequence and an infinitely small sequence is an infinitely small sequence. Let x(n)th be a bounded sequence and a(n)th be an infinitely small sequence. We want to show that the product is an infinitely small sequence. Since the first sequence is bounded, there exists some positive number such that for all n, this inequality holds. And let's take a positive epsilon. Since the second sequence is infinitely small, then for the positive number, epsilon divided by a, there exists such n large that for all indices after it, the absolute value will be less than epsilon divided by a. This is by the definition of an infinitely small sequence. We know that the absolute value of a product is equal to the product of the absolute values. For n more than n large, we know that the first term is less than or equal to a, by definition again. And the second term, we know that this is strictly smaller than epsilon divided by a. Therefore, we can rewrite this into a multiplied by epsilon divided by a, which is equal to epsilon. Thus, for any positive number epsilon, we have found such n large that for every n after this n large, the absolute value of a product is less than epsilon, which is the definition of an infinitely small sequence. A direct consequence of this is that the product of a constant and an infinitely small sequence is also an infinitely small sequence. Alright, today we explored the concepts of bounded and unbounded sequences, and then focused on infinitely large and infinitely small sequences. We used precise mathematical definitions and proved key theorems about their properties, understanding how these concepts relate to each other. In our next video, we'll move on to one of the most fundamental concepts in mathematical analysis, the limit of a sequence. The ideas we discussed today about infinitely large and infinitely small sequences will be essential for understanding limits. Thank you for watching.